This is, can you believe it, our last week of school. Oh my gosh. So I do want to make sure that you notice up here your homework. This is the right page, page 57. I know it seems kind of crazy. So this is review of complex imaginary numbers and their operations. And then these problems here on page 559 are the new objective that involves your complex number skills. So ignore number 1 of the warm-up. So this problem was an objective that we skipped this year. So writing the polar form of a linear function is something that you can look up, you can Google, you can Khan Academy if you like, but we skipped that objective this year since I didn't want to load you up with your last weeks. So go here to number 2, write an expression in standard form. Standard form of a complex number is a plus bi, where remember a is the real component, right? B is a real number, but bi is the imaginary component. Because remember, complex numbers is the union of the real and the imaginary, right? You can't be both real and imaginary at the same time. Complex numbers is the union of those two numbers. Remember from AAF that by definition, I squared is equal to -1. So when I ask you to clean this up here, I'm asking you to find all the real numbers. Well, that's a real number there. But isn't this a real number? 6 times I squared, isn't that 6 times -1, which is -6? And then what do I have here? I to the 4th. Do you remember our patterns? I to the 0 is equal to 1. I to the 1st was equal to I. I squared was equal to -1. I cubed was equal to I squared times I, which is -I. And then I to the 4th, we were back at 1 and we repeated the pattern. So I to the 4th is the same as I to the 0. And I to the 0 is 1, so this is just a positive 6. This is a -6, plus 6 times -1 is a -6. Then, of course, I have 4i and 2i. But what do I have here, right? Negative square root of 25, well, that's -4 times 5i. Remember, suck the negative out, suck the I out front. So that's -20i. And now I've taken care of everything. 3 plus 6 is 9. 9 minus 6 is still 3. So I have 3. Then I have 4 i's, 2 i's, and -20 i's. So isn't that negative, what, 14? If I'm doing my math right? Sorry, I lost 6. Yeah, -14i. Okay. Now, I want you to be careful here. 2 minus I squared is not equal. You cannot distribute a square across, right? That's 2 minus I times 2 minus I, which is 4 minus 4i, right? Because that's minus 2i, minus 2i, plus I squared. But what's true about I squared? That's right. So this is 3 minus 4i. Awesome. All right. So Our objective for this, actually the next two lessons are going to be on complex numbers and polar forms. So you're going to need to perform arithmetic with complex numbers. We just reviewed that. But we're going to plot complex numbers and we're going to convert complex numbers to polar form. Right? I told you when we were back in AAF and we dealt with imaginary numbers and introduced the imaginary numbers as a way of identifying zeros or solutions to polynomials that were not graphable on the xy plane, right? So you had a parabola like x squared plus 4 is equal to y. Well, there are numbers you can plug in for x squared, add 4 and equal to 0. They're just not real. Hence, the parabola did not touch the x-axis. Before we get to that, though, let's do some more review. So the handout that had the warm-up problems on it, and we'll have these next review problems on it. You can pause the video and do yourself, but I'm going to do a little bit as well. So 3i squared, the expectation is again that you know that's a -1. So this is -3 minus 4i plus 7 plus 2i. So you're going to join the real parts together and the imaginary parts together and get 4 minus 2i. This is multiplication, so you have to make sure to distribute. Clean that up. What is that? That's 2i. So 2i times 3 is 6i, and 2i, positive 2i, minus I is -2i squared. But remember, I squared is -1, so I have this 12. This is a real number, and this is a real number, right? That's 2. So 12 plus 2 is 14 plus 2i. Oh my Lanta, what's going on here? Right, this is where we have to remember our pattern, right? I to the 30th. Think about writing out I 30 times and chunking by 4 because our pattern repeats in 4s. Or just take 30 and divide it by 4 and you get 7, which I don't actually care about the 7, right? 7 times 4 is 28. I care that I had a remainder of 2. This is in your notes from AAF. Little book, go look it up. So the remainder of 2 means that this remainder replaces the exponent of 30. So I actually have I squared times 3 minus I. But what is that? I squared is -1, so I just have -3 plus I. So I have -1 times -I. Truth? All right, next. Some more review. Write each complex expression in standard form. Remember, we don't really divide complex numbers, right? In this form, we just get rid of i's in the denominator. First, I'm going to clean this up, and I cubed is the same as -I, isn't it? And I taught you how to get rid of this last year, and I told you to remember this pattern. This is going to be 2 squared minus 1 squared. I'm sorry, plus 2 squared is not 2, Laura. 2 squared plus 1 squared in the denominator, and then this I just have to distribute. There you go. Or you, of course, write this as -8/5 I plus 4/5, or if we're going to put it in standard form, the real part goes first. Okay. Let's do this next one. Now be careful with your order of operations here. Before I even deal with this denominator, I'm going to clean up the numerator. Exponents first. I cubed is negative I, but negatize negative I, and that's a positive I. 3 plus I squared, remember, is 9 plus 6I plus I squared. What is that? That is 8, because I have an I squared, which is a negative 1, so I have 8 plus 6I all times I over 4 plus I. But isn't that 8I minus 6, right? Because I squared again is negative 1 over 4 plus I, but what do I need to do here? Four squared plus 1 squared, and then I need to multiply that. So what do I get? 32I minus, check my math here, minus 24. 32 minus 24, and then negative 8I squared, and minus 6I. So what do I have? Negative 8I squared is positive 8, minus 24 is, what is that, negative 16. And then I have 32I minus 6I, so what is that, 26I. Whoops. Over 17. Let's say I'm not confident in my answers, especially when you're at home, or if you're on an assessment where you're allowed to have your calculator. Let's go to your calculator. And check out some of these answers, right? So what do I get here when I've got 4I cubed divided by 2 minus I? Ah! What is that? Oh, 4/5 minus 8/5 I. What up now? Pretty cool, right? Let's check that last one. I'm sorry, yeah, the last one I did. 3 plus I squared times negative I cubed whoops, that's a 1, isn't it? Divided by 4 plus I. Ah! Oh, look. Negative 16 over 17 plus 38 over 17I. So I made a mistake in my math, right? Somewhere here. Oh, look. Negative 6 times negative I is a positive 6, right? So it was worth my while to check my work here. So but I wanted to get out the calculator. I purposely didn't do this last one because I first want to look at it on the calculator. So 2 square root of 3 plus 2i all cubed. Whoops, sorry. Oh my goodness. Cubed. Well, that's a nice number. Wait just a second here. What's happening? First thing I want to do is make sure I go correct this work. Right? I distributed the -6 to the -i, and I wrote -6i, but it should be positive, shouldn't it? And so now I have a 32 plus a 6i, so this should be 38i, which is what my calculator said, right? Now, we've already talked about the square, so cubing this does not mean you distribute the cube. This is 2 root 3 plus 2i plus 2 root 3 plus 2i plus, times 2 root 3 plus 2i, right? You have to multiply that all out. Or, since it's a cube, remember you can do this. Pascal's triangle and do the binomial expansion. So this is 2 root 3 cubed. This is 2 root 3 squared and 2i to the first. 2 root 3 to the first, 2i squared. 2 root 3 to the 0, just like there's actually a 2i to the 0 here, and a 2i cubed here. Expand that out, collect like terms, and you know what you're going to get? 64i. It was super nice to do on my calculator. But I want you to remember this problem after we learn something about complex numbers and polar form, and think about, without a calculator, how I would have either had to remember Pascal's triangle and binomial expansion rules, or I would have had to just do algebra here and remember to multiply these two together and then distribute the third factor. Either which way, I would have combined like terms and I would have gotten 64i. Would have taken kind of a lot of work algebraically. Not a lot of work with a calculator, but algebraically, a lot of work. All right. So your handout that I gave you, I think I did all the problems on there. I think there was a C that I did that was different, and a that was a little bit different. No, I'm sorry, I'm looking at the wrong one. It's all good. So this was all reviewed. Most of the beginning of, on that page 57, is all review of complex numbers like this. But now on to the actual objective. Plotting complex numbers. The number 1 plus 2i. Now I know that seems like that's a single entity, 1 plus 2i. Where does it go on the number line, right? Where do I put it? This is the real number line. Where does that belong? I can talk about the number 2, and I can talk about the number 1 on the number line, and I can talk about 1 being bigger than 2, right? It's farther away from 0 on the right. But how do I think about plotting complex numbers? What kind of number line do I put those on? And can I talk about how much bigger one is than the other? How do I think about that? Well, instead of the XY axis, I'm going to draw a rectangular system like this. I'm going to call the horizontal axis the real number line and the vertical axis the imaginary one. Woo, kind of weird, right? So I'm going to call a complex number z. I have a complex number, I've named it z, and z has a real component and an imaginary component, and a and b are both real numbers. I can also, of course, just change my variables and call the real part x and the yi part the imaginary part, and think of x and y, though, as real numbers. So going over to the axes, if I plot the real number on the real number line, I go in a horizontal positive or negative direction. And the imaginary part, I just think of the I as telling me to go up, right? The I just says I'm on the vertical axis. And I count up y units or down y units and then plot that point. This z, this point is x plus yi, or a plus bi, and it is the union between the reals and the imaginary. This is called the complex plane or the Argand plane after mathematician, along with Gauss. Gauss and Argand did there's one more too, that did a lot of work with the complex plane. The magnitude, right, when you want to think about bigger, the magnitude of a complex number is, yep, come on in. Ah, Pythagoras, yep, welcome back, good to see you. The magnitude of a complex number is Pythagoras. It's the distance from the origin. There you go. So, how would you compute the magnitude, if I call that complex number 1, the magnitude, yes, you can think absolute value, is the square root of 1 squared plus 2 squared, which is the square root of 5. What is the magnitude of complex number 2? Sure, it's negative 1 squared, but aren't they the same size? So to plot this number, if I was actually plotting 1 plus 2i, I would go over 1 in the x direction and up 2. That point is 1 plus 2i, and z, the absolute value of z, or the magnitude of that complex number, is the square root of 5. And if I were to plot 2 minus I would go to 2 on the real axis and down 1 vertically, and the magnitude didn't do very well with my scale there, but the magnitude is also square root of 5. Crazy, right? We do call this the absolute value, but in complex number land, modulus. is a vocabulary word that you are responsible for. Modulus is the absolute value of the complex number, or the magnitude of complex number. Think magnitude modulus. We don't really say absolute value very much. We either say magnitude or modulus in this arena. Also, standard form, it's so annoying that these words are over this, standard form of a complex number is also called rectangular form. And it's called rectangular form because we kind of used, it was very analogous to the XY plane, right? The rectangular Cartesian plane. So A plus BI, where you think of X and Y, the real and number line and the imaginary number line. X and Y is kind of rectangular, right? So practice these two, right? Plot 4 minus 6i and find the modulus. Plot -1 plus 7i and find the modulus. Okay, here's my real number line and my imaginary number line. So pause the video or just go along with me. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And the modulus. Which is 16 plus 36, or the square root of 52. If you were, that's fine to leave it like that, but if this was multiple choice, you would see this as 2 root 13. Because this 52 is 4 times 13. Let's do the next one. Let's say that was Z1 and this was Z2. -1 and up. 1, 2, 3, 4, 5, 6, 7. This is Z2. And this modulus is the square root of 1 plus 49, or the square root of 50, which in multiple choice would be written as 5 root 2. Okay? Graphing in the complex plane. Woot woot! Oh, I don't know why that's supposed to be hidden for now. Now, polar form of a complex number. So not plotting a complex number, polar form of a complex number. So remember, A plus BI we call standard or rectangular form. But I can represent that same complex number using R's and theta, which is called polar form. This is rectangular, X and Y. And again, sometimes we use A and B, doesn't matter. Rectangular form. But remember in polars how we define X? X is R cosine theta and Y is R sine theta. And again, if we think about this as the real number line and this is the imaginary number line, and we go over an X and up a Y, and we graph this point, this is Z is equal to X plus YI, and we talk about the modulus. We can also talk about how we went over an X distance, up a Y distance, Therefore, there is a theta that we rotate to get to the modulus, which in polars we call the radius. Oh, my Lanta. Now, I'm going to factor this r out front. And the polar form of a complex number looks like this. R cosine theta plus I sine theta. The short name, or the nickname if you will, is complex number z is r cis theta. Some people make that a hard C and say kiss, but weird. I say r cis theta. And it's the radius cosine I sine theta, and the theta is the same, right? So here's the cool nickname for the polar form of a complex number. So let's practice with some of these. Oh, sorry, yes, don't forget some formulas that shouldn't seem, right? Shouldn't seem strange to you. The absolute value of z is actually the radius, and it's equal to, hello, Pythagoras, he was still here. And of course, theta is equal to the inverse tangent of y over x, but remember, you have to think about what quadrant you're in. The inverse tangent of y over x really just gives you, right, the theta that's inside this triangle. Excuse me. So you have to figure out what quadrant you're in, which is why you need to know how to plot them, so you can figure out which theta is appropriate. The angle theta is called the argument of the complex number z, right? Theta is called the argument of z. You don't have to use that, you just have to recognize that vocabulary if someone uses it with you on an assessment. All right, so let's look at these. So I want you to convert a rectangular complex number, where this is A and this is B, or X and Y, right? So to go to polar form, I need R, R is the modulus of the complex number. And theta is the inverse tangent of 32 over 32, which conveniently is 1. But first, I have to think about the quadrant that I'm in. I know that the inverse tangent of 1 is pi over 4, but I have to graph this and make sure that I'm in quadrant 1, am I? If I go over 32 and up 32, yes. And that should make sense to you. That this angle is 45 degrees, or pi over 4 radians. And it's kind of back and forth as to whether you answer these in degrees or radians. If your directions don't say, then they have to take either answer. I tend to stay in radians simply because we use radians so much in calculus. So here, notice that I've used the exact same values, except negatized 32. So R is going to be the same, isn't it? Theta looks like it's going to be the same. Negative 32 over negative 32 is asking for the inverse tangent of 1, which is pi over 4. But when you graph this, what quadrant are you in? Negative 32 and negative 32, you are in quadrant 3. Right? So, what is my theta when I'm in quadrant 3? It is a pi over 4, but how many pi over 4s is it? 5. Oh, I forgot to finish my problem. Right? I didn't finish putting this into polar form. I just found my 2 answers. So, the polar form, z is equal to r cosine pi over 4 plus I sine pi over 4. Or, if you're cool like that, this is 32 root 2 cis pi over 4. And what's this one? Right, and that should make sense. All right, how about the next one? Square root of 4, which is 2, right? And I just want the positive because I'm talking about a radius. And this time it's the inverse tangent of 1 over negative root 3. I don't even really care about the negative because I just plot these here and I say negative root 3 is negative 1 point something, right? Negative 1 point something and 1. What quadrant am I in? I'm in quadrant 2. 1 over root 3 is a pi over 6 issue. Which pi over 6 is in quadrant 2? So, z is equal to r cis theta. What do I have under there? Good grief. Oh, can't even read it. So this one is 5 minus 12i. So I'll do this up here since I can't get rid of this. R this is a Pythagorean triple, right? R is equal to 13. And theta is equal to inverse tangent of 12 over 5. Again, I don't care about the negative. Right? 12 over 5. Okay, use it or don't, but plot it. Plot the point. Where am I at 5, negative 12? I'm in quadrant 4. So if I use my inverse tangent here with negative 12 over 5, I am going to get the right angle, but it's going to be negative, right? Because inverse tangent is defined in quadrant 4. So I get out of here, and I put this one in degrees just because this wasn't a special angle, and I got 67.4-ish degrees. Negatized, because I'm going backwards, right? So z is equal to 13 cis, and we don't, it's not, I guess, technically wrong to write negative 67. We just don't, right? Give me, this is why an AAF, right? Give me the positive coterminal angle to that. and it's about 293-ish. Just rounded it to the whole number, which is fine for now. Okay, so r is always positive because it's a magnitude, right? It's a radius. And then your theta just has to reflect being in the appropriate quadrant, right? So I did a quadrant 1, a quadrant 3, a quadrant 2, and a quadrant 4 problem. Now let's see if you can go the other way. Convert z is equal to, and if I were to write this in shorthand, 22 cis 5 pi over 6. Right? It's in polar, go back to standard. So how do you do that? Well, speed trig. What is the cosine of 5 pi over 6? 5 pi over 6 is in the second quadrant, right? Cosine is negative in the second quadrant. Pi over 6 goes with root 3. Cosine goes with root 3 over 2, negatized. Sine 5 pi over 6. 5 pi over 6 in the second quadrant. Sine is positive in the second quadrant. Pi over 6, sine of pi over 6 is 1/2 times 22. So this is negative 11 root 3 plus I over 2. And if you were to graph that, negative 11-ish and 1/2. All right, let's do one more. Again, speed trig. Can't be taken too long to do these to figure out what this is. The cosine of 4 pi over 3. 4 pi over 3 is in quadrant 3. Both cosine and sine are negative. Cosine of pi over 3 is 1/2, but negatized because I'm in quadrant 3. Sine 4 pi over 3 is root 3 over 2. Again, negatized because I'm in quadrant 3. And then multiplied by 20. Negative 10 minus 10 root 3. Crazy, crazy, right? Oops, I forgot an I, didn't I? All right, so that's it. Again, the first part of your homework is a bunch of just review problems with your complex arithmetic, right? Making sure that you square and cube things correctly. Remember I told you to highlight one of those problems on the review sheet where we got 64I. I'm going to refer to that in the next video lesson. All right, take care.